Recall the ruler we built. They fixed the standard hydrogen electrode at 0, and against it copper measured plus 0.34, while zinc measured minus 0.76. So every electrode got a definite number. Today we will simply use those numbers. They will line them all up, predict which reactions run, and calculate the cell potential. Attack every electrode's standard electrode potential in order, from the most positive at the top to the most negative at the bottom. This ranked list is called the electrochemical series. Hydrogen sits right at 0. Everything above it has a positive standard electrode potential, and everything below it has a negative one. The species at the top, with the most positive values, grab electrons most readily. These are the strongest oxidizing agents, and fluorine is the strongest of all. The species at the bottom, with the most negative values, give electrons most readily. These are the strongest reducing agents, and lithium is the strongest of all. As we go down the table, the tendency to grab electrons falls, and the tendency to give electrons rises. The rule is simple. A higher, more positive species grabs electrons from the lower one, and that reaction is spontaneous. Zinc sits lower, so it gives its electrons to copper 2+. Zinc plus copper 2+ gives zinc 2++ copper. That is why you cannot store copper sulfate solution in a zinc pot. The zinc dissolves, copper deposits, and the pot is ruined. To find a cell's voltage, we use one formula. The standard cell potential equals the cathode potential minus the anode potential. But the cathode, reduction happens and it grabs electrons. But the anode, oxidation happens and it gives electrons. Take the Daniell cell. The standard cell potential equals 0.34 minus, in brackets, minus 0.76. Minus a minus becomes plus, so that is 0.34 plus 0.76, which equals 1.10 volts. When that is exactly the Daniell cell's 1.1 volts, the same bulb that lit up back in part 2. A positive standard cell potential means the reaction is spontaneous, so the cell is a galvanic cell. One more example. For the copper-silver cell, the standard cell potential equals 0.80 minus 0.34, which equals 0.46 volts. The same formula works for any cell. Suppose we want to oxidize iron 2+ into iron 3+. The iron 3 plus iron 2 plus value is plus 0.77, so we need a species sitting above plus 0.77 volts. Anything above that line can do it. For example, chlorine at plus 1.36, permanganate at plus 1.51, and dichromate at plus 1.33. The standard electrode potential values are also used to find the pH of a solution, the solubility of a salt, the equilibrium constant of a reaction, to carry out precise potentiometric titrations. So quick recap. The series ranks every standard electrode potential. The higher species grabs electrons from the lower one,